All right, so we're going to start talking about signals today. So start off with, we think about a modern language like Java. When I say exception handling, what do I mean? What are we doing with exception handling? What's its purpose? What problem does it solve for us, etc.?
If like something goes wrong with the program, don't just kill the program, catch the exception and maybe throw an error message, but other things can still run.
Okay, so is it fair to say that the exception handling is an opportunity for us to have a program either gracefully crash or gracefully recover from something that would have otherwise crashed it?
Yeah, that's a more elegant way of saying it.
All right, so gracefully react to, let's call it, bugs isn't, let's call it crash conditions. I like that. Gracefully react to crash conditions in such a way that we can give reasonable feedback or even recover. Now, maybe we would see this, I'm sure most of you have seen some of this at some point now during the semester, but one of the most frustrating things you can get in C is just a segmentation fault. Have you seen those before? So segmentation fault basically says something went wrong, probably dealing with memory, but maybe not. So it's not very instructive what went down. All right, so typically exception handling is done inside of a try catch where we have pre-identified code that might be problematic, and we try to execute that code and then catch issues that arise. So we're going to call that's kind of the more modern, we'll call this modern signals. Or at least one use of this is modern signals. Because signals are actually a form of interprocess communication, but our first use of signals is going to be to allow a program to be aware of something bad occurring before it, well, as it's occurring, instead of the program just crashing with a segmentation fault. All right, so let's go over here and let's look at a couple of examples. So I want to look at main 1C. All right, so here is a plain Jane computer program where we're just doing some math. We have a couple of integers, 121 and 0, and we're trying to set result equal to 121 divided by 0, okay, which is a bad result, right? Bad things will happen when this occurs because you're not allowed to divide by 0. Actually, interesting example here, unrelated to this particular example, but earlier I saw a video that I guess you can ask Siri to do something divided by 0, and Siri has like a comeback joke or something where they say, assume that you have 0 pieces of pizza or something like that, and you divide that evenly among 5 people or something like that. How many pieces of pizza do each of you get? Then it calls you an idiot or something like that. It's like cyberbullying from Siri. I don't know if it still works, but apparently that was something that used to work on Siri at the very least. So at some point, ask Siri to, divide something by 0, do like 31 divided by 0 and see what Siri does. But in any case, we're doing some bad math here where we're going to take 121 divided by 0 and bad things should happen. So let's look at this. So that was the program main 1. So I'll compile that. All right, so we get this floating point exception, and then we get this core dump thing, which doesn't sound good. But the program ungracefully crashed. We had no input or anything like that because we had some bad arithmetic stuff go down. All right, now an alternative to this is if we use signals. So signals live inside of signal.h. And what we do is we write a handler for this. So this is just going to be some function. And this is the function that we want to have called when the bad thing occurs. All right, you can name this whatever you want. We just happen to have named this one handler underscore divide by 0 because that's what it does. It handles divide by 0 problems. All right, but this guy does need to take in an integer, which is probably going to be the signum, the signal number that arises in case you want to have a single handler that handles multiple possible signals. You can say if signum was this, this is the bad thing that happens. If signum was something else, this is the bad thing that happens. Similar like in Java where you can have a try with multiple catches. So in Java or C#, you can try to execute these 30 lines of code. And let's say within those 30 lines of code, 5 or 6 bad things could potentially occur. With that in mind, you could just do the generic catch exception. And whatever bad thing happens, you just handle it inside of that single catch. Or you could choose to have 5 different catches, for example, where you gracefully respond to each different thing that could go wrong because maybe you're gonna respond differently to each one of those. All right, so that's probably the more appropriate thing to do is to have a catch for every potential exception so that you can handle that exception with some directive. But at the end of the day, nothing says you can't just, in fact, I usually just write a catch with a single exception in it when I'm teaching just to save lines of code, save time, that kind of stuff. But in professional programming practice, you probably want to correctly handle your exceptions. All right, so this is our prototype for our exception handler. It returns nothing and it takes an int. The name of it is unimportant. All right, then we have our main method, same stuff we had before. We are creating a void pointer here. You'll see how this is used here in a second. So this is used with our signal processing. So we're going to have our signal handler return the value that comes from that. And this is going to be associated with as our constructor, so to speak, for a signal, where we say the type of signal we're dealing with is a sig FPE. So again, all capital letters. This guy is probably, well, he's a macro that probably associates with an integer. If I hover over this, this he's associated with the number 8 for no good reason. And this is an erroneous arithmetic operation. And this lives inside of signal.h. And let's see if I can. See if it gives us a list in here with descriptions. I have a web page set up, but it doesn't really have descriptions of the possible things. So here's sig FPE. Let me try to do this. Linux signal list with meaning. All right, well, this gives us maybe some common ones. All right, so we can get a signal interrupt, and we're going to actually see that when we look at using this as an interprocess communication. This allows you to find out that another process has died or quit naturally. These two, signal interrupt, signal quit. We just looked at the floating point value. Signal kill means an external entity killed it. So maybe somebody did a PS, did a top to get the process IDs, or did a PS-AX to see all the running processes. Then they did a kill on one of the running processes. So something would then fire the kill. Associated with timers, we can have that a timer is done. That would be another example of inter-process communication if we want to have multiple processes all tuned into the same signal listener and say, hey, look, I want to know when some event occurs, some alarm happens, something like that. So we'll go back in here. So we're creating a signal around this signal code, and we want the handler for this to be the name of our function that we wrote, handler divide by 0. All right. This if statement just says if something went south when we tried to create that signal handler screen. So this is just error checking around handling the signal. Otherwise, we're going to go ahead and do our math like we did before. So in a newer language, all this stuff would be kind of like in a try catch, where we try to do something and we catch at the bottom. Instead, what we're saying is that inside of main, anything can go wrong. This whole thing is kind of our try. And we've set up a signal handler here that says, if a very specific thing goes wrong, in this case, arithmetic signal, then call this guy rather than crashing out with whatever the default handler is. All right, so here's our handler for divide by 0. Again, it takes it a signal num. And I mentioned earlier that you might choose to have a single handler that responds to different signals. So for instance, in this one, we're asking if the signal that was passed in is equal to the floating point thing, then we're going to say we received the divide by 0 exception. I think signal FPE actually responds to any arithmetic math problem, not just divide by 0. I'm trying to think what other problems would be prevalent, but any problem falls into that category. All right, and then we have an else that says, look, some other signal occurred and this is what I received, but wasn't expecting it or something like that. But nothing keeps us from having a single signal handler and then having a whole bunch of if statements to say, if it's this error, do this. If it's this signal, do this. If it's this signal, do something else. So on and so forth. All right, so let's go look at this code run this and see the exact same thing, but how it actually catches the exception, so to speak. Notices that it was a SIG FPE and then prints out that it received this signal divide by 0 exception, proving that it's handling it for us rather than just doing the whatever it was, the core dump thing. This dude, floating point exception, core dumped. So we'll do GCC main with signals. I'll not put extra characters in there. And we have our A dot out. So notice we got a received SIG FPE divide by 0 exception. This was our handler receiving that signal, allowing us to do something different, or in this case, the program just ended, but we at least didn't have this generic error message where we don't really know what went down and just crashed. All right, so this allows us to associate specialized handlers for various signals. And I do have the list of signals. Let me close this ad blocker thing. pulled up here. Again, I don't know what all these signals do. You would have to look up specific ones, but you know, we have 64 unique signals, it looks like, in this list. And I guess I'm not even necessarily sure if that's exhaustive or if this is the 64 common signals, because I know you can make up your own signals if you don't want to respond to common things. So in any case, we have these built-in signals that hopefully cover the base for whatever you want to do. Let me scroll down through here. All right, so another example. So let me actually just paste this one in. This is having a program raise a signal. Okay, so purposely raise a signal. So in our previous example, the operating system is raising that signal, right? They're saying, hey, you tried to divide by 0. I don't like that. I'm raising a signal. In this case, we're raising a signal ourselves in our code. So I'll just create another new file here. We'll call this guy raise signal.c. All right, we're just printing out what we're testing, and then we use the raise function, which came from signal.h, to raise this specific signal. All right, so we got this signal raised here that if somebody else was listening, they could have interjected there. We'll keep going through these examples, but that's how we can have a program specifically raise a signal, kind of looking down the line for inter-process communication when we want to let another process or a collection of processes know that something has occurred. All right. Now we can create a handler for that guy where we're actually handling it ourselves, I suppose. So we get a process ID from right here. In fact, actually, let's do the code for this because we might modify this particular one. Let's call this raise and handle.c. All right, so we're going to have our process ID type here. And we've seen this before with the, what system call have we used before that gave us our process ID type?
Fork.
Yep, the fork system call. And the fork system call returns an integer. What are the possible integers it returns and what does each one mean?
Isn't it like 0 is the child and then anything greater than 0 is the parent?
Okay, yep, so if it gives you a 0, because remember, fork creates a clone of the current process at the same line of code. So when the fork system call returns, it gives you a 0 if you're the child, because after you call fork, you're probably going to ask a question. You're going to say, who am I? Am I the parent or am I the child? And the answer to that question is probably going to dictate what you do next. You do the stuff the parent should be doing, or do you do the stuff that the new child process should be doing? All right, but in either case, those guys will give you a process ID type. Typically, things that have an underscore T on the end of it are actually placeholders for, like, let's say, fake types. These are enumerated types or a type def. So we see that a process ID is actually just an int. But this gives us a type associated with it to kind of clue us in on not just did we name this variable PID such that we expect it to be the process ID, it actually is a process ID type, which is just an integer, but we've actually done a second level of flagging. All right, so this particular process is going to get its own process ID, and that comes from this Unix standard library. This is where we can get our own process ID. I'm pretty sure that's the case. Hold on a second. Yeah, it's in Unix standard library. Returns the process ID. All right, so this process will become aware of what his own process ID is. Then we're telling it what to type, and we'll see that here in a second. So it's this program is finding out its process ID, so it can tell you the process ID to type in to kill it. All right, because that's the command to kill off a process. So he's going to get his own process ID. Tell you to type in kill from a different terminal. It'll then raise this signal. And this signal says, I'm capable of, I scream about this signal. That's what it says. All right. So these two print statements here tell you what, as a human being, we can type in another terminal window to externally stop this process, externally kill this process. Then this process here is saying, look, I'm keeping my eyes open for this signal, because if I get that signal, then I want to respond to it, kind of almost on my deathbed type thing. All right, so this guy will block. This is a blocking line. I'll show that to you real quick. So what do I call this one? Raise and handle. GCC, raise and handle. We'll go ahead and run that guy. Well, it is blocking. It's just not letting me show that it's. So I'll go ahead and copy this. Was it shift? Ay. And I'll do it this other window here. So I'll kill that process. And now that I killed that process, if I go back over here, notice it said it received that signal. If I go back into code here, that line was right here. That didn't happen until this guy finally received that signal. So after I told it what to print, I raised this signal stop thing, but this is saying stop and wait for this signal. Okay, does that make sense? Stop and wait for sig stop. Once it actually received that signal, I could then choose, we're kind of doing a setup here for the handler that we expect to receive this thing. We haven't written it yet, but we can choose to associate this signal with our, so if I want to come down here and define this function here, I could do something like printf in the handler. Now we'll see by default here, this guy will not get called. So let's go run this. This will still compile. All right, so it's waiting for it. It's 26439. 26439. that, come back over here. It's received the signal, but it didn't get into the handler. Okay, in order for it to get into the handler, we needed to use the signal function to associate that guy with our handler. And we can do this here, stealing what we did before. I'll just copy this line and we'll adjust it over at our other code. The name of my function is this guy. And the function, this is sig stop. All right, so I'm going to use the signal function to associate this handler with this signal. All right, now that I've done that, if I come back out here, compile it again, run it, it's 26723. Hold on, did I not fully associate it? Give me a moment. Oh. This guy is not going to raise it himself now. It will be raised for him. The only reason I got to this line is I didn't comment that out. Oh, but it's not going to get killed because it's still running. I need to just put it in a while loop. Waiting forever. While true. Actually, I think C will let me do that. Want it? So the capital T. Is that standard lib? Where does true live? Somewhere in there we have the placeholders for true and false. True is 0, false is non-zero. So I'm just saying do nothing, but just keep spinning. You might like that look of that better, but this body of this has nothing in it. So I wait forever on this guy for it to be externally killed off. I think this should accomplish what I wanted to accomplish. It did not. Oh, hold on. That's false. That's true. False is 0. True is anything other than that. So this original thing I had in here should work. Okay, there we go. So that guy's sitting there and spinning 27469. So we've killed off that process. Oh, it didn't receive it. not kill off the process? 27469. Maybe we got to do a sudo. So sig cont says to continue, but my process is clearly not dying. Let me do a top over here. Here's my A dot out 27469. And it's using 100% of my CPU. 27469. Okay, so that did kill it, but it didn't raise the signal. I'm not going to be able to show it this way. Oh, wait. I'm doing sig stop over here in my code, right? Sig stop, yep. One moment. Okay, we'll run that. 27954. Run 954. Okay, so that did stop. Okay. Now we can come back in here and we can raise sig stop. I think this is the way it'll end up working. Two 28138. Let me make sure that guy is still running. It's not. I got to be doing something stupid. Let's just keep going through their example here. Now they're implementing that handler. Sig T STP. Is that a trigger stop? Okay, so that's through the terminal. Sig T STP. Sig T STP. We do still raise it. We don't raise it. Yeah, make sure we raise the correct one now. PSTP. The source is coming from our terminal, not another program. Sig stop would come from another program. All right. One more college try now. All right. Although that's already in the handler because we raised it. All right, so that's sitting there and spinning. 28786. So I actually think that we two eight seven eight six. Is that it? 28786. All right, so it did terminate, but it didn't get us into our signal because we didn't actually raise that signal. So 28929. Big TSTP. There we go. All right, so just had to make sure we had the right signals lined up here. So now in our code, our signal handler is going to be associated with a terminal source signal stop. So this particular number, which is a 20. And what do? We call this guy. Then we go off and now we do our thing. Our program's running. We don't raise the signal ourselves. Instead, we're just sitting here. We're stuck in an infinite loop doing whatever we're doing. Then if an external entity comes along, like we did here, and we say to kill that process, we actually catch, because I think, let me just make sure, I think it's still running. We catch that signal. As part of that kill command, that signal was raised and the process didn't actually die because we caught it and handled it ourselves. So in this particular case, if an external process tries to kill our process, we could decide, well, we're going to let it kill us, but we are going to, I don't know, back up some information or something like that first. Similarly, I can, let's see, what's the command? Just exit. Standard lib is just exit. So I can come in here into my handler and I can run the exit command with some return code 0. Do I have standard lib? It thinks it knows about it. Maybe it's not in standard lib. So now when this handler gets called, I'll print out something, but that'll also tell the program to kill itself. So I've intercepted the kill command's raising of that signal. As I currently have it, I called this function and it just went right back to my loop that was sitting here spinning. Now I'm going to say, well, I'm handling it, but I'm going to go ahead and tell my program to die off anyways. We'll see if this compiles on its own. Otherwise, I have to import standard lib. Yep. Okay. All right, so now it's running 29576. Two nine five seven six. Kill that. Come over here, waiting for everything the handler, but then it did exit. All right. So what we did with the signal is we intercepted that signal, handled that signal in our code right here. What does the signal say to do? It just says to print out this text, but then it says actually kill this program. So this is what killing something ultimately does. But this gave me an opportunity to interject something in between in case I want to, in case I want to back up some files or something like that, rather than just letting this thing die. All right. Now, the next step would be, and this is where we were going before, is I can say sig stop like that. I'm going to steal, actually, I'm just going to steal this whole code here. So this guy's going to listen for a sig stop, which would come from another program. All right. And then he's going to go and do his wait for everything, whatever, then he's going to get his handler. So I'm going to create another file here. We're going to call this guy raise sig stop.c. Paste stuff in here. I don't need this line. I don't need this line. Don't even need, well, whatever. I will raise sig stop. This, and we'll just do a printf. Raising sig stop. All right, so this program, all he does is raise sig stop. So this guy's running, he's an infinite loop. Right, not put it in the same. No, I did. All right, so that guy rose that signal. Oh, we need to raise it to a certain. Since we're not grabbing on to the signal handler using a unique key like we did with all of our shared memory stuff, right now my only way of getting out of process is to raise that. I would need to identify the process directly. All right, so we're going to need to use a key in order to accomplish this the way we want to accomplish it. All right, so we got this one done. Let's see where they get their key. This is still coming from the terminal. We want to do this from another program. And I'll set up this example for next time, which we're just about out of time. we should get a unique identifier for a key. Because ultimately, what we want to have is we want to have two running processes where one process sits there and waits for a signal from the other one raises that signal, communicating, inter-process communication, and this guy knows that that signal was meant for him. So we need to have a unique, and it's probably done with this struct, but I really thought you had to identify a key with the signal handler. Maybe I'm just missing it in here. In any case, I'll get an example working for a process killing off another process. And then what I ultimately want to do is I want to write a merge sort with signal processing for when things are done with a different thing. So we want to spawn off, we're going to use fork to spawn off child processes, where child processes will sort their own little portion of the collection. And we'll probably keep our array inside of shared memory. So this is going to be like a super merge sort. So we'll have our array in shared memory. We'll have multiple processes, each working on a different part of the array for sorting it. And then when each process is done, they're going to let the parent know that they have finished their little part. And then what will happen is once all the parts are done, then the parent can do the final merge step. But that all should happen pretty quickly since we're using multiple processes in order to do the merge sort instead of having a single process. So recursion for merge sort isn't all that efficient when you're doing it with a single process. But if you spread that over multiple CPUs or even multiple computers, merge sort is a distributed sorting algorithm. So us creating that protocol for us using shared memory for the source of our data, using signals to let us know, let other processes know when we're done, and then using fork to spawn off child processes to work on a different part of the array will be a fairly ideal solution to merge sort. And I think it should be fairly intimidating. All right, so we'll stop it there. Any questions, comments, concerns about kind of the beginning things with signals? All right, I will see everybody on Friday.